I just want to welcome you all. My name is Austin Hollopeter, and Joe Cicero is also here. We kind of help get the ball rolling on this, and we're really excited just with the journey that quantum computing has come along and just the different connections that we've been able to find and make. And we're really excited to kind of get this started in the region and start making connections with, everyone who's working on this. We know we have some great people at CASE, some really good companies that are doing some amazing stuff in this space. So really excited to get the conversation going. This is virtual right now due to COVID and everything, but we're hoping to have these in person going forward. And let's go to the next slide. Okay, so format and expectations, we're going to have 20-minute presentations from each of the speakers, and then we'll have 5 minutes after that for questions. Feel free to add questions in the chat throughout the presentations. We'll be monitoring that, and we can kind of collect those if you have any questions and present that at the end. And we just want to put out thanks to the Cleveland Big Data Meetup group, especially Doug Meal and Chris Barrett. They've had a very successful meetup. If you get a chance to visit them, they have some really great content, and they helped us kind of put this format together. They've seen a lot of success with it, and we're hoping we'll see the same. Okay, so to go over the agenda, we're going to have a quick quantum computing level set with John Marcsik, and then we'll get into our main speakers, data science and quantum computing with a Forge demonstration, and that will be with Sean Weinberg from QCWRU. Unfortunately, Steve's not able to make it tonight. We'll also have quantum state entanglement with focus on quantum key distribution and quantum communication with Chris Papachristou from Case Western Reserve University. And then Robert Loredo from IBM will be doing 2 presentations, one for a quantum roadmap, Qiskit runtime, and quantum machine learning. And then he'll be doing an IBM composer demonstration. So really looking forward to that. If you are not aware, you can today work on a quantum computer. So that'll be really exciting to see. We also have quantum inspired algorithms with Shui Zhu from Case Western Reserve University, which I know you've done some exciting stuff there. So excited to see what you have for that. And then just a few announcements we wanted to make. So from QCWRU, if you get a chance to go to their Q2B conference, I think you guys are going to have it live in person this year. But I know Joe and I got a chance to go out to that. It is a fantastic conference. It's going to be December 7th through the 9th at Santa Clara Convention Center. They're going to have major presentations from all the big players in the quantum space. Just a great chance to connect and meet with people who are like-minded in researching and understanding the potential of quantum computing. As far as for CASE, they are planning to offer a course in quantum computing at CASE again this next spring semester. Some of us got a chance to see the presentations from their students this year. A lot of great stuff, really interesting discussions regarding quantum computing. So if you're interested in learning more, check out their course offerings. IBM is offering a 2-hour intro and walkthrough demo of quantum computing by 2 of their quantum ambassadors. That'll be August 12th, 12 p.m. to 2 p.m. I have links in the registration. I'll put some of these details in the chat as well. And then just a general notice that there's an NSF conference coming up in just a few days. If you get a chance, my understanding is that it's free to attend, and there should be some really interesting presentations there as well. Okay. And then John Marcsik is going to give us a quantum computing level set. John, I'll let you take it from here.
Okay, so welcome to Quantum Computing 101 in 10 minutes. Why quantum computing? What problems might quantum computers be good at? Historically, the first quantum algorithm that got people excited about quantum computing was Shor's algorithm. Shor's algorithm is a quantum algorithm that allows you to factor very large integers into its prime factors. What is that good for? Generally cryptography. Encrypting information sent over the internet is the major idea. The major idea there is that a classical computer has a hard time factoring these large numbers, and that makes skipping some details, of course, but it makes the encryption solid. The pickup there is very large. You'll hear people use words like exponential pickup or super polynomial pickup. It just means very fast. You'll hear people talk about what you can do in one day on a quantum computer, maybe take 10 billion years or something. That's that kind of a pickup. Another area that quantum should be good at is chemistry. Molecules, which are the basis of chemistry, obviously are quantum mechanical objects. Classical computers have a hard time computing different aspects of the way molecules work. Generally, when you have lots of electrons, there's lots of interactions between all of the electrons, and it's very hard to compute. However, it is quantum mechanical, so there's a fairly simple way to map these problems onto quantum computers, which is also quantum mechanical, and to use that quantum mechanical speed up that you get, again, to get a very large speed up on those types of problems. The last type of algorithm I wanted to talk about here is the prototype is Grover's algorithm. Grover's algorithm is a much more general idea than, say, Shor's, which is very specific, and it gives you exponential speed up. This is only a quadratic speed up. What does a quadratic speed up mean? It means that, say, a classical computer would take 10,000 iterations to do something. A quantum computer would only take a square root of that. So square root of 10,000 is 100. So again, in that example, it's a pickup of 100 times. So it's still very significant, may be very commercially valuable. And Grover's algorithm is somehow less specific to a certain type of problem. It's more sort of a general characteristic of quantum computing. You can use it for optimizations problems like machine learning, or operations research, which is like routing problems and things of that nature. Also, if you have a computer simulation of a probability distribution that you can take samples from, a method called Monte Carlo method, say for option pricing, you're sampling from some distribution of, say, stock prices, and some statistics, say in this case, the average of that sample is going to give you an option price, or in risk management, where maybe you're looking at a certain percentile of a distribution. The smallest part of a quantum computer is called a qubit. A qubit is simply any quantum system that can be measured to be in one of two states. They're usually labeled with zeros and ones to be analogous to classical computing, where we reference a bit, which is generally thought of as the smallest bit of information, can be a 0 or 1. Notice the notation. If you look at the first bullet point there, we label the 0 state with a vertical line, then a 0, then a greater than sign. That's to clearly note to us that that is a quantum state, not a number. So it's the quantum state of 0, quantum state of 1. How are quantum states different than numbers or a classical qubit is that you can put these qubits in a superposition between 0 and 1, so that there's some probability of measuring the system in a 0 or measuring the system in a 1. When you measure the system in a 0 or 1, you can output to a classical computer the result of that measurement, so 0 or 1. So the output of measuring a qubit is just a normal bit. It can be picked up by your laptop if you're doing something in the cloud, in the quantum cloud. But the state inside of the quantum computer is a superposition of the 0 and the 1 state. So there's some probability you'll measure 1, some probability you'll measure 0. So you can think of those as weights, and those weights can be used for computation. Something a little bit harder to understand is there's also an angle. If you're in a superposition, there's an angle between the 0 state and the 1 state called the phase. And although we can't directly observe that phase because it doesn't show up in the probability distributions, it will show up in a probability distribution sometimes if we apply an operation first to that state and then a measurement. So that's how we can infer that these angles are really there, and we can use those angles for computation as well. You can't do a whole lot with one qubit, so let's look at multi-qubit systems. If you have 2 qubits, then you can measure the first qubit in a 0 or 1. You can measure the second one in a 0 or 1. So that's a combination of 4 different outcomes. And of course, these are quantum states. So you can, all quantum states can always be put in a superposition of the states. Again, those are weightings that are going to give probabilities that the results of both of those measurements will be either 0, 0, 0, 1, or whatever have you. You can see on this slide there's also a 3-qubit system there where you can measure 0, 0, 0, 0, 0, 1, etc. There's 8 possible outcomes. So when you consider these superpositions, the multi-qubit state, the 3-qubit state, is more information, has a bigger computational space than 3 qubits separately, because 3 qubits separately, each one of them can be in one of 2 states. You would think you could add them up to be 6 total states, but here you get actually 8 total states. So there's some extra information that appears in a quantum system because of this, the fact that you can put basically a weight on each of these possible outcomes. That extra information that's not in the individual qubit states determines what is called entanglement. So you can entangle qubits. You can, if you had a 2-qubit system, you can entangle both of those qubits. It's a relationship between the qubits. You can see it in the total distribution of the results. So you could have a system of 1 qubit that has a 50% probability of being a 0, 50% 1, another one 50-50. When you put them together, there can be a correlation or a relationship between those. So you can arrange it as in this picture so that if you measure one to be in a 0 state, the other one has to be in the 1 state, or vice versa. So entanglement can be very complicated if you have a large set of qubits. This space of weightings and these angles, it grows exponentially, basically like 2 to the n. So this little chart shows you just how fast that computational space grows. So if you had, say, a 100-qubit system, if you think about all the ways they can be entangled, I mean, that's more pieces of information than we could ever imagine a classical computer, at least in the near future or foreseeable future, could be. So this giant computational space is the hope for quantum computing. What's the catch? So everyone's heard of catch 22. I call this catch 2 to the 22. So if quantum computers can do all this great stuff, you know, why haven't they taken over the world yet? Shor's algorithm is over 25 years old, and we're still waiting to see some demonstration of that algorithm that beats, you know, a laptop. So what are the challenges? It's hard to overstate the challenges in quantum computing, unfortunately. The first is complexity. So if you're going to have a great algorithm, you're going to want to create a very complex, very entangled state on your quantum computer. However, you can't get there from starting with a completely simple state, which is the way we start the computation. In other words, to get to that complicated state, we have to do operations called gates on just 1 or 2 of the qubits at a time. You can't apply a very complicated gate to like 100 qubits at once. That's just not the way the system works. So it could take a lot of gates to do your algorithm, in which case you might lose any advantage over a classical computer. That's getting information into the system. Getting information out is also hard because all these weights we've talked about and all these angles, these phases that we talked about, you can't directly observe them. What you have to do to get the weights out is you have to run samples over and over and over and get a probability distribution out. So you have to measure the qubits many times to get distribution. You can imagine if you have 2 to the 1, if you have a probability distribution on 2 to the 100 weights, you have 2 to the 100 weights, then you want one specific weight. If it's close to a uniform distribution, it would literally take you forever to estimate that weight. So that's hard. The key is to find an algorithm that exploits what's called interference. So you have this giant superposition in your system, and when you apply gates and these operations you do, you're basically adding quantum states to other quantum states. So if you want to emphasize a state, you make sure their angles, the phase between them will be 0 or close to 0. And if you want to de-emphasize them, you want to make sure their phases are close to 180 degrees, so they basically cancel each other out. Sometimes you'll hear the words constructive interference, destructive interference. So the goal would be to have a very complicated state, use destructive interference to get rid of all the information you don't want, and to make a high probability you measure the information you do want. The other last 2 things are more hardware related. Multi-qubit systems lose coherence, so all the information in your quantum system and your complicated state that you took forever to create can very quickly disappear if it interacts with anything in the environment, like a stray piece of heat or whatever. We need some error correction, which we're still waiting on the world to create. And lastly, hardware is very hard to scale. You can imagine as each of these little systems very hard. You have to be able to apply gates to each qubit, and you arrange them in a grid. You have to have a way of scaling up all the controls for that. Thank you.
Thank you, John, for the quick Quantum 101. So now we'll go right to our first speaker, where Sean is going to speak about data science and quantum computing with a Forge demo. Sean is a quantum engineer at CWRU with a PhD in physics from UC Berkeley. He focuses on quantum algorithm research and enterprise engagement at CWRU. Sean, if you'd want to take over the screen, you can get started.
All right, thank you very much. I'm going to go ahead and share. Okay, so can everyone see my screen here? And hear
Yes,
me?
it looks like. And then if you want to go ahead and get the slideshow started on there. Excellent.
How's that?
Okay, looks good.
All right, yeah, so feel free to just kind of interrupt if there's questions. I mean, we have questions at the end, but you know, if there's something that you really want to get out really quick, you can just interrupt. So primarily, I'm going to be talking about a product that we're developing at CWRU, which is called Forge. It is a quantum software as a service platform. Given what you just heard about the foundations of quantum computing, it might seem a little bit crazy that there can already exist like a software platform that gives you access to quantum computing, but we do have that. And you know, the thing to understand that you should just have in your mind is that the hardware is not ready yet in quantum computing, but that doesn't mean that we cannot start building an algorithmic framework and a framework that gives people access to quantum algorithms for commercial applications. And then we can kind of build that in parallel with the evolution of hardware. And eventually that should create value in a commercial sense. So keep that kind of strategy in the back of your head as you're understanding this. Before I get into talking about the platform, I'm just going to say a few things about the side, sort of business side, and give you a sense of the kinds of like use cases that we have, that we do at CWRU. So CWRU wants to create value with quantum computing. The problem is that right now you would need an immensely large number of very fault-tolerant qubits, a quantum computer that does not yet exist. So that will improve as hardware manufacturers make better qubits and more qubits. What CWRU does, what our company does, is we try to reduce the burden by designing better algorithms that require fewer qubits, that require, you know, qubits with better noise tolerance. So we make algorithms that are more error resilient. And you see, CWRU as a company, we design these algorithms and then we sort of apply them in a commercial settings. That's what you could call solutions. And then we sort of give this to a customer through our software platform, which is called Forge. And I'm going to give some demonstration of that today. And then one more thing, which was mentioned, is that we host a workshop called Q2B. You can go to the website here, q2b.us. This is just a quick little overview of how Q2B has been growing. I've had a great experience both times that I've attended Q2B. The last one was virtual, but fortunately the next one should be in person. You know, obviously we'll be monitoring the situation with COVID. And you can see my greatest accomplishment in life, winning one round of quantum chess at Q2B. Okay, so let's talk about industry collaborations, because when I first was joining CWRU, it was really amazing to me, the notion that, you know, a quantum computing company could even have customers in industry. But once you sort of understand what a company could be looking for in a quantum engagement, even at this early stage, then you can sort of understand how it makes sense. So what it comes down to is that companies want to sort of create a plan for the fact that quantum computing is growing. And we sort of phrase it as like a timeline. Like a company would first kind of develop a internal working group and maybe attend a conference. They might then sort of start forming their internal education, make a partnership with other companies that specialize in quantum computing, and then sort of try to find a use case that's relevant in their industry, execute a project, and then eventually they could move on to hiring quantum experts and then, you know, proceed forward in more advanced directions. So we sort of imagine this timeline that a lot of companies might want to approach because they're trying to sort of prepare for the future of quantum computing. It's sort of like an insurance policy. We have lots of customers. These are some of them. I'm just going to give you a quick little overview of a few of the kinds of use cases that we've encountered before I get into the Forge product, just to give you a sense of the types of problems that commercial partners are interested in. So with Goldman Sachs, what we did was basically derivative pricing, you know, like call option pricing, for example, and this is done using quantum Monte Carlo techniques. Unfortunately, because of the short time limitation, I'm going to move through these a little bit rapidly, but you can ask questions about it at the end if you'd like. Airbus is one of our important partners. They're interested in issues of, you know, they have to validate that the logic trees on their software do not have any faults, that there's no like unexpected behavior when you do something. And that's a very complex mathematical optimization problem. It turns out there are quantum algorithms for mathematical optimization problems that are relatively near term. So we did analysis of that. We also did a flight path optimization problem with Airbus. That was somewhat less successful than the fault tree analysis. And that's sort of one of the things that, you know, people want to learn is what problems are, you know, really well suited, what problems are less well suited. Another important partner of ours is Covestro, and I don't have too much to say about this except that with Covestro, this is chemistry simulation. So this is like mapping a molecule onto a quantum state in a quantum computer. We also did drill path optimization with Equinor. Not too much I want to add to that, just you know, understanding, you know, paths of drilling and optimizing that with quantum algorithms for binary optimization. Another important partner for ours is a company called Aishin in Japan. So Aishin is a big automotive component manufacturer. We did two major types of projects with them. One involved essentially static code testing. This is similar to the fault tree problem. It's an optimization problem. The other problem that we did with Aishin Group is a logistics optimization problem where we optimize the logistics of trucks carrying parts to factories. So as you can see, there's lots of, one more with BMW, we also did a routing optimization. So there's tons of different types of projects that various partners are interested in exploring. And, you know, you can go into a lot of analysis of what the sort of most reasonable applications are, and what, you know, the real motivations behind companies are for wanting to get their foot into this door. There's a lot of discussion to have there. But for now, I do want to move on and tell you a little bit about our software platform, which is called Forge. So Forge is it's a software as a service. And it primarily focuses on quantum algorithms. It also provides hardware access, but the main selling point of Forge is actually the unique and performant quantum algorithms, while the hardware access is, of course, sort of available through partners like Amazon, AWS Bracket, IonQ, Rigetti, D-Wave, and so on. One thing that you should understand about Forge is that it actually targets two different types of users. One is what we would call, or we sort of use the phrase, quantum engineer. The quantum engineer is someone who has learned a bit about quantum computing, understands what quantum circuits are, wants to manipulate quantum circuits, run quantum circuits, either on like a simulator or a GPU accelerated simulator, or on actual hardware. The other type of user is a data scientist, and a data scientist is someone that maybe they don't actually feel like learning, you know, They don't feel like learning how to actually write a quantum circuit. They just want to run their data set on a quantum algorithm. So we provide API calls that give access to what, you know, the sort of businessy phrase is turnkey algorithm. So turnkey is in like turn the key on your automobile and it just turns on without a problem. That's the idea of the data science user here. They don't have to worry about the details of the quantum algorithm. So Forge targets both of these users. And I'll kind of mention how there's sort of tools for both of these types of people. Really quick, for data scientists, we offer algorithms for binary optimization, machine learning, Monte Carlo sampling, although that's actually a roadmap item that is going to be added soon, and also linear algebra. For quantum engineers, we offer tools for loading classical information into a quantum state, utilities like the ability to, well, if you're familiar with something called QAOA, which is a quantum algorithm, and don't worry about it if you're not. If you're familiar with that, there's these angles that are kind of like weights in a neural network, and we offer utilities to find such angles. We also offer tools to sort of translate between different circuit languages like Qiskit and Cirq. We offer simulation tools and just ways to more easily build quantum circuits in a convenient fashion, sort of cutting and pasting, stitching circuits together, and so on. We have a family of different backends available, D-Wave, IonQ, Rigetti. We have simulators as well, CPU and GPU simulators. And this is just a quick picture of what Forge looks like. If you want to see it yourself, just go to forge.qcware.com. This is a sort of top level overview of the structure of Forge. You can see that, you know, we have the main point of it is the applications and algorithms, and it functions through a variety of partners. So we use a sort of circuit editing and translation middleware, and then send that over, for example, to Amazon Bracket, which then sends it to Rigetti, for example, to run on their quantum hardware. So that's just sort of an overview of the sort of software structure of Forge, a very simplified overview. Okay, let me kind of, at this point, push into some demonstration in the interest of time. I think we're probably under 10 minutes left here. So first of all, let's do some linear algebra because this is a really easy place to start and it's simple to understand. If you're a Python user, then you probably use NumPy a lot. If you're a machine learning person, you might use PyTorch or TensorFlow. But instead of these on Forge, you can use something called forge.qutils. And this gives, this lets you do sort of standard linear algebra calculations like dot products and matrix multiplication and distance measurement. But it gets the results using a quantum algorithm. And that quantum algorithm is either a simulator or hardware. So let me show that to you. Give me just a second to. The only problem with Steve not being able to make it is that it's harder to switch between the slides and the demo. So can everyone see my screen here where I have the Jupyter Notebook open? Okay, so I'm just going to show you how this works. So you're looking at Forge right now. You can see that on Forge there's sort of a standard web app here. You can look at API calls. You can see your API key, which you can use to run things locally, support, and so on. You can also look at backends, which I'll probably show you in a little bit. But to run things, let's say that I have two vectors, 1, 0, and 0, 1. Those are perpendicular, so the dot product between them should be 0. So all that I'm going to do is just qcware.qutils.q dot of AB. And indeed, the answer is basically 0. See the E minus 16 here. So it's essentially 0. So that actually ran a quantum that just ran a quantum algorithm in a simulator. And you might say, okay, well, like, who cares I can just run this on NumPy. But the point is that you can use these simulators to better understand how the quantum algorithms behave. And then you can also actually run this using hardware as well. And I'll show you how to do that. So you can do this with much bigger data on the simulator, like 100-dimensional vectors. You can do this for matrix multiplication. So I'm going to take A and B as n by n matrices, 4 by 4. I'm going to get the matrix product. And here you can see I'm just comparing the result from NumPy and the result from Q dot, and it's the same as expected. And then finally, I just want to point out that you can actually run this on hardware as well. And all that you have to do is say backend equals AWS bracket / IonQ. So by adding that backend string, you get access to the physical quantum hardware. And that's sort of a core concept in Forge, that you first can run things on a simulator, then you can say, okay, now I want to do it on hardware. We also have a distance estimation function. This is a very similar idea. So you have 1 and 5. The distance between 1 and 5 is 4. If I run this, I get 16. That's not a mistake. It's that it's actually computing the Euclidean squared distance is all. You can do this on higher dimensional vectors. And again, you can run this on hardware. And there's also more advanced functionality for batches of vectors and so on, if you want to get into fancier linear algebra. So again, you can run this on hardware, and that's sort of one of the main points. Let me just really quickly, we're kind of low on time, so I'm just going to show you a few things right now while I have this open. So if you take a look right here, this is sort of our list of backends. And you can see that we have these different backends along with these QCT multipliers, which relates to pricing. And you can just look at these and figure out, okay, I want to now try running my problem using the TN1 tensor network simulator, or I want to try running it with Rigetti. And that's kind of how this works. So let me pause here and ask, am I sort of out of time now, or do we have a couple more minutes?
I believe you have 3 more minutes and then we'll have questions.
Okay, great, thanks. I'm going to return to the presentation. Can you see the presentation?
Yep.
Okay. Okay, let's talk briefly about quantum machine learning, another important application in quantum computing. It's important to realize that we are at an early time still, and quantum algorithms still take longer. The time to solution is still longer than the classical approach. But as hardware progresses, quantum algorithms can do computations much faster than classical algorithms can. So eventually, you would hope the quantum algorithm will be superior. So we focus on having more efficient QML implementations than other services do. So in particular, for example, one of the key points with quantum machine learning is that you have to first start by taking all this classical data and encoding it into a quantum state. And we've designed these special data loading quantum circuits that very efficiently load up quantum information. Let me very quickly show you a classification and a clustering algorithm, depending on how quickly I'm able to get this swapped over. Okay, so this will just give you one more idea of what this software can do. I'm going to do classification with a quantum algorithm called Q nearest centroid. This is a quantum version of the classical nearest centroid classifier. So a very basic machine learning algorithm, not deep neural network or anything like that. So take a look at this data here. The colored X's are labeled data points, and the black circles, those are unclassified data points, and we'd like to classify the black circles. So we'd like to color them basically. To do this on Forge, all that you do is you use this QML.fit and predict, and then you say, okay, the algorithm that I want is Q nearest centroid, and the backend that I want is CPU simulator in this case. So you run that. You get the labels, and then I'm just going to visualize the result with Matplotlib. And you see, all I did was I colored the data points. It's intuitive, it makes sense. And you can then run this if you wanted on IonQ. Really quick, I'll show one last thing. I mentioned data loaders. This is kind of fun to see. So imagine that I had some data. Here's some data points. And now what I'm going to do is I'm going to use these data points, these 4 numbers, this 4-dimensional vector, and I'm going to make this circuit. And I made this circuit with this call loader of data, and that creates this quantum circuit. Now that I have this quantum circuit, let's see what state vector this circuit generates. If you look, it generates a state vector with these complex amplitudes. And if you look back at the data, like minus 0.21 here, it matches an amplitude in the state vector. So the state vector reconstructs the classical data. And that's one of the tricks that we use in order to do quantum machine learning. And just to show you, we actually have 2 different types of loaders. We have this parallel loader, which uses more qubits, but less circuit depth. And we also have what's called an optimized loader, which uses fewer qubits, but greater circuit depth. That's the cost. The cost of reducing the number of qubits. So I'm definitely out of time now. Sorry about that. Yeah.
I should put up my little clap symbol.
Yeah, sorry about that.
Excellent, Sean. That was a great presentation and demonstration. I know. I think we had a question in the chat that I think Fabio was able to answer.
Yeah. So yeah, Fabio is our QC services lead. He just hopped on the call, I think.
Yeah, awesome. Does anybody have any questions that they want to ask right now?
I actually have one. Oh, sorry,
okay.
Go ahead. I didn't find any raising hand over there. So my question is, I checked your website and your pricing is not cheap. So if I start as a developer, I understand that's free, but for companies and other stuff, are you taking care of the back end on running the quantum algorithm per minute that you included in your plan, or is it do I have to pay the Amazon or other D-Wave companies, because they charge companies too?
That's so if you are a QCWRU Forge user, then the only thing that you pay is our fee, because we are then paying the hardware provider. So now I will mention perhaps one small caveat, which relates to IBM, because of the current nature of our service agreement with IBM. With IBM, you would basically have an account through IBM that you then just use Forge as a tool to run through that account on, and then you would only pay IBM. But that's actually just a red herring. That's an exception. For all the other services on Forge, you only pay us, and all that we're doing is we are just passing over your payment to the hardware provider for the service, and then of course taking whatever our share of it happens to be in that case. So the answer to your question is no. You would not have to pay, say, Rigetti if you ran a Rigetti problem through us.
One more quick question. Sorry to take everybody's time. If IBM or Amazon decides to change their backend or API, because I'm assuming that you're using their sort of SDK to connect to their system, because they don't let you to connect directly. So if they change and come up with some new algorithm or optimization or noise correction, are you if you use your system, do we have to wait, or is it just transparent? You're using their API, and then every updates that they have is going to be affected yours too.
Yeah, so we try to be as efficient as possible with that, or our goal is to be as efficient as possible with that. So we will, generally speaking, want to avoid those types of delays. Obviously, as you know, the nature of software engineering is that things can be very unexpected, and you can have curveballs thrown at you. But as our business is growing, I think that one of our main goals is going to be to avoid that type of trouble where you would have to have a delay. But yeah, we can't make any definitive promise that if Amazon changes something, that we'll immediately be able to reflect that. If you're going to use Forge, then you should probably think that you want to use Forge because of certain unique capabilities provided by Forge, not just because you want to use a tool through Forge. So I see a hand raised from.
Yeah, we'll take this. Will be our last question. Andre, go ahead.
Oh, this is kind of like a stupid question, I guess, but on the last thing that you were covering, I was a little confused on what you were doing. So you're somehow putting classical information into a quantum circuit. Could you go over that again? I was just
Yeah. So sorry, I have to apologize that I don't know how familiar you are with like quantum computing and quantum mechanics. So my answer to you might be a little bit generic, but essentially we're taking classical data, classical information, and we're storing it in a quantum state in some form. In this case, we're taking a vector of classical just numbers, and we are creating a quantum state whose coefficients, whose amplitudes match those numbers as well as possible.
Thank you for that answer,
could you
Sean.
go behind the mechanics of that? Oh, sorry.
I'm not sure if Austin wants us.
Yeah, unfortunately, in order to keep us going at a good pace, I'm going to have to cut it off here. But I just wanted to put a note out there that we will be putting out some resources for for those who want to learn more about some of the fundamentals. That most of us are new to this, and it's a journey of learning. So we'll be posting more resources in regards to learning more about this stuff. If you do continue to ask questions in the chat, and I know that Fabio and some of the others of us can answer those as well. All right, and then our next speaker is Chris. It looks like you. Sorry, Joe, I'll let you.
Yeah. Sorry. Yeah. Our next speaker is Chris. He's going to be talking about quantum state entanglement with a focus on quantum key distribution and quantum communication. Chris is a professor in the Department of Electrical and Engineering and Computer Science for Case Western. And Chris, if you just want to take over, you can take over the share.
Yeah, I'll share the screen.
And we'll give you a couple minutes, Chris.
Okay, is it shared?
Yep.
Okay, and then we get into the full screen mode. Okay. All right.
Awesome. Thank you.
So my lecture, my talk is a little bit much more generic and much more academic than the previous one, which was great. And but I will be focusing on something different from quantum computation, not much different. Quantum communications and networking. In fact, according to some experts at least, quantum communications is more near-term to be achieved than big quantum computation, although both are dependent on the nature of quantum mechanics, etc. Anyway, so this is the agenda. That's kind of, I will go fast. I have planned a review, which I will go really fast, okay, on quantum states, but I will, in my review, I will focus a little on spinning electrons, as this is a good way to look at how really the quantum states are, represented in practicality. And then I will talk about the main part of my talk, which is the entanglement and the entanglement distribution, and how do we do that in a quantum network. So I will discuss Bell states and multipartite entanglement, and I will then discuss some applications, particularly teleportation, one of the famous quantum communication applications, quantum key distribution based on entanglement, and quantum repeaters, and so on. Okay, this is a more generic actual picture of the actual hardware, where we use magnetic spin of electrons in order to represent quantum states. And there are three axes here, X, Y, Z. So we have spins in either direction along the axis of X, Y, Z. And these are represent quantum states. More specifically, here we have a spin under the magnet. If you want essentially to affect the spin, to influence the spin, then just put generically a magnet. Of course, this is done in practice in a different way, but let's put a magnet, in an electron and a magnet, and then you can have the spin going up or going down, depending on whether the magnet is north poles, south or up. Okay, and you can have actually the electron spin in a different direction, in the X spin direction rather than Z spin direction, and then you can still have the spin influenced by the magnet in both ways. But this represents different actual states and different bases in the quantum. In the Z spin axis direction, which is up and down, essentially this represents the quantum states, generic states or basic states, 0 and 1, okay, in the Dirac notation, which the previous speakers explained. And in the X spin direction, which is essentially a rotation by 45 degrees, Then again, you have 0 and 1, except that these are in the Hadamard base, essentially, and they're rotated. And you can have superposition states using essentially the two basic states. Now, superposition states are formed and they can be measured. However, this destroys them, essentially the state itself. As we say, it collapses the state because essentially superposition projects the direction into the direction of the basis. In this case, the basis is the direction up and down, the z direction. So essentially superposition will project into that direction. And more specifically, a state which is described in superposition of the two basic states, the zeros and ones in quantum, then it's projected in either of the two states, either 0 or 1, with probabilities though, which depend on the squares, actually square, and because A, alpha, and beta are complex numbers, the squares of the magnitude of these complex numbers, these are the probabilities, they sum up to 1. Now, we have essentially two essentially qubits, two electrons spinning, okay? And if they have no interaction, suppose their electric fields are far apart somehow and they don't interact, then we form this way, depending on the direction of the spinnings, we form 4 states, okay? And this is up, 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 down, and so on, 4 states, okay? And then the joint state can be expressed in a quantum way, in Dirac notation, this way, okay? And it consists, essentially expressed as a superposition of the 4 basic states, which are 0, 0, and so on. And each one, if we measure, which is a projection into the direction, again, of the basic state axis, if we measure any of these joint states, we will have essentially a probability of 25% in order to receive any of the 4 basic states. Now, this is I will skip this, basically I say what I said in the previous slide. Now here we have the spin entanglement. If the electric fields of the 2 electrons are close by and they interact, then there is a chance that we'll have entanglement of the 2 electrons and they will have an entangled state. Okay, as you can say, the spins interact. What does an entangled essential state mean? Well, here we can see it better. The entanglement produces essentially a correlation between the 2 spins, the blue and the red spin. And the joint state is essentially a superposition of the 2 states, 0, 0, and 0, 1. And this is a deeply entangled Bell state action, okay? And if you do a measurement of this entangled state, there's a probability to receive, again, either 0, 0 or 1, 1, the 2 basic states, with probability being 50%. This is a review of the gates. Okay, I will skip this. And here is the Bell states, which are very important in quantum communications. And these are the 4 Bell states, which can get from the electrons we showed before, depending on which way, essentially, the original preparation of the inputs are done. This is the circuit, the quantum circuit, which produces, schematically at least, any of the 4 Bell states, provided that you have prepared the inputs appropriately. So if you prepare the inputs 0 and 0 at the input, then you will get this state, which is the famous EPR state. Okay, I will not get into that. There's historical argument about this, but it's one of the famous Bell states. But there are 3 more, which you can get by preparing the inputs, for example, 0, 1 here, or 1, 0, or 1, 1. You'll get all 4 Bell states by proper preparation of the inputs, okay? Now, this can be implemented with spins. It can be implemented with photons. I didn't talk about photons, so I'll talk later, but with a photon apparatus, for example, a photon splitter, you can entangle 1 photon by parametric, so-called parametric down conversion, produce 2 photons entangled into a Bell state. So it's possible to do it in a number of practical ways to produce Bell states. These are fundamental states to do quantum communications and a lot of other things also. Okay, now here is the first application, which surprisingly can be described with 1 qubit, can be done with 1 single qubit actually. Okay, and this is quantum teleportation. Basically, teleportation of this means that one originally prepared quantum state at, we call this teleportation character traditionally Alice and Bob. So if Alice prepares a state, has a state in the beginning, a Q state, a 1-qubit state, she can teleport the state into Bob. Essentially, we have regeneration of the state at Bob's side. Now, there are certain conditions for this protocol, okay, which we'll describe. And first, there's a public channel, which essentially a fiber optic channel, which connects Alice and Bob. So Alice can communicate to Bob using essentially bits, classical bit information to Bob, okay, and vice versa possibly, okay. Now, there's a third character here, an EPR character, let's call him traditionally Victor or Charlie sometimes. And this character prepares an EPR pair, the Bell state essentially we discussed before. This can be done photonically. Actually, you will need to do it photonically because you'll have to send the qubits to Alice and Bob, and that the only technology that makes sense. And so it will prepare an entangled A and B qubit, okay? And Victor sends qubit A to Alice and qubit B to Bob. Now, A and B, because they're entangled, they keep their correlation no matter how far they go. If one goes to the moon, still it's correlated to the one on Earth. That's the beauty of entanglement. So now, in implementing the protocol, Alice has 2 qubits, qubit Q, which is the original qubit she wants to transfer, and qubit A, one of the 2 entanglement pair. And Bob has only 1, qubit B, okay? However, there are 3 qubits on the map here, A, Q, A, and B. So there's a joint 3-qubit state which Alice actually forms, but she controls only Q and A. She does not control B. Bob controls B, okay? So what Alice does, and I will show the circuit in the next slide, she performs a Bell state measurement on Q and A, okay? She measures Q and A, essentially, which will destroy Q because the state is projected, essentially, to the axis. So Q, the original Q, is destroyed. Not before, of course, Alice gets the result of the measurement. And because there are 2 qubits, Q and A, there will be essentially 4 results, 4 projections, okay? And the 4 results, Alice encodes, and this encoding has been a priori agreed with her and Paul, Bob, and she encodes the resultant state in one of the 4 states of 2 bits. And she sends the 2-bit code to Bob. Again, Alice measures Q and A, produces a state, and she looks at the state, after the measurement, she knows the state, okay, of the measurement, and she sends the corresponding coding to Bob in classical bits. Okay, so Bob receives the code in classical bits, and depending on the code, he performs a Pauli operation. Okay, Pauli operation I showed earlier, but it's essentially a matrix operation, 2x2 matrix operation. And he performs a quantum operation, either a Pauli gate, essentially, X, Z, Y, and I is essentially the identity matrix, on qubit Q, okay, on qubit B, which he has, okay? He performs this operation on qubit B. So there essentially could be a chance of 4 different operations to be performed. And depending on the operation, all of them will generate qubit Q, the original state, which has been already destroyed. So the original state is teleported using this methodology from Alice to Bob. It cannot be copied. Yeah, you may ask, why don't you copy and send it by photonic? The no-cloning theorem prevents copying, unfortunately. It's one of the restrictions of quantum theory, but we cannot copy a quantum state. But we can teleport the quantum state, which is great. So let me show the circuit of this implementation, okay? Alice and Bob teleportation. Basically, first we prepare the Bell state. These are the qubits A and B, which are entangled after we, pass them through the circuit. So at the output of the circuit, A and B are entangled. Q is the original state of the Alice qubit. Now, Alice receives one of the 2 qubits, A, and Bob receives the second, B. So Alice gets A and has Q. As we said earlier, Alice will make a measurement, okay, on qubits Q and A. First, she disentangles the qubits, and then she does classical, these measurements. the measurements will produce essentially 2 states, okay, which can be encoded with 2 bits. So all this area here represents the experiments that Alice does. Okay, so once Alice finishes the measurements, 2 bits are sent through the public channel to Bob. Here is Bob, and Bob performs the XYZ operation. Okay, now the X and Z gates, these are quantum gates, are controlled by digital bits. Okay, so depending on the state, essentially the output will be Q, the original qubit, the original qubit state that originally Alice had. So this is, in simple terms, the teleportation operation. And the communication, 2 communications here, if we go back, which are done. There's a classical communication. However, let's not forget that the 2 photon qubits need to be sent to Alice and Bob. So we need a quantum channel, essentially, to send A and B to Alice and Bob, respectively. Now, the core of the talk, actually, entanglement swap. Okay, first the concept. We discuss the entanglement. Suppose we have 4 qubits or 4 particles in general, which could be photons or something else. Okay, A, B, C, and D. Suppose these are actually in some station, some nodes of a quantum network eventually. Okay, they're located. And they have been produced. Okay, now suppose also that we arrange the distances of these quantum stations in such a way that A and B, B and C and D are nearby in the sense of less than 10 kilometers, actually, and I will explain that more. But A and D may not be so nearby. So what do we do in order to do a swapping? We first entangle the pairs A and B and C and D, which can be done even in parallel under certain conditions. So now we have A and B entangled and C and D entangled. Then we do a Bell state measurement between B and C. Now, B and C are not very far away, less than 10 kilometers, so we can do this Bell, it's feasible to do this Bell state measurement, which we do. As a result of the Bell state measurement, 2 things happen. B and C are entangled, and A and D are entangled, okay? So A and D are entangled, although two points here. First, A and D are not so close. They could be actually very far away, depends on the distancing. Second, A and D originally were not related. They didn't know each other, yet now they are, okay? That's the important thing about swapping the entanglement, which essentially is propagation of entanglement. So this is the important point. A and D have no relation, had no relation or history, yet after the Bell state measurement, they are entangled, okay? And they have relationship. Now, we can easily expand this idea to entangle lots of nodes, thousands of nodes, okay? And we can do chains of entanglement, cascades of entanglement, or we can do it, some research we're doing in a hierarchical way also. Okay, suppose there are groups of essentially qubits originally. The first group, number 1, the first group, number 2, number 3, number 4, and they are in nearby distancing located, but so this way you can understand better. So the first group, number 1, are these qubits. The second is number 2, these qubits, and so on. Now the distancing of adjacent qubits is near in the sense of less than 10 kilometers. That's magic number I will explain. Okay, so you can continue this with group number 5, 6, etc. So you can cover lots of nodes, thousands of nodes. So what we do here is first we entangle the nearby qubits in every group. So in the first group, we entangle 1, A1, B1, D1, C1, and so on, okay? Then we do Bell state measurements within each group, as we did before. So we do Bell state measurements in the first group, in the second, in the third, in the fourth. This could be done potentially in parallel. Now, as a result of the Bell state measurements, you actually produce entanglement swapping between A1, D1, A2, D2, 3, and 4. Now, second Bell state measurement among groups, okay, between groups. So I will do Bell state measurement between C1 and B2, and so on. So between C1 and B2, I do a Bell state measurement, and also another Bell state measurement between C3 and B4. As a result of these Bell state measurements, new entanglement swapping will appear, as shown. And A1 and D2 nodes are not so close at all. They may be far away, quite far. And they didn't share any history earlier, yet now they do. And also 3 and 4. Now, while stopping here, we're doing another Bell state measurement between C2 and B3. Okay, as a result of that, we have entanglement of the faraway nodes, A1 and D4. Okay, and this can continue hierarchically to cover the whole network, the whole internet, perhaps. All right, now let's see some time estimates here of this with assumptions, with data taken from a lot of researchers and experimenters, because these data are a little bit, to some extent, not definite yet, depends on whoever technology and whose experiment. So there's some variations in the data. So first, in this essentially protocol, the hierarchical entanglement swapping protocol, what we do Bell state measurements, and then second level Bell state measurements, and third level Bell state measurement for the example we have on the screen. In terms of timing, if L is the common distance between the adjacent nodes, which is less than 10 kilometers, and V the speed of a photon connecting A1 and B1, essentially the speed of a photon in a fiber line, in a fiber cable, which is 1/3 of the speed of light, something like that, approximately. So then the first timing, T1, on the first level of entanglement is this formula. I will give some numbers in the next 2 slides. The second is this, the third is this. Assuming that the Bell state measurement is approximately the same, then the overall formula is this for the time. What is the time? The time required in order to do the overall entanglement here, entanglement swapping, or entanglement propagation, or entanglement distribution, similar terms. And this is logarithmic into the number of nodes, actually, okay, which is good. All right, let's discuss a little bit, because the technology to do this entanglement swap. Yes.
Sorry to interrupt your flow. I know we're at the 20 minutes. I'm going to go ahead and let you use your 5 minutes of question time just to finish up the slides.
I'm already there. Okay, then I will skip this cavity. Cavities are used for memory. It's a nice figure, but I will skip it. It says in some detail how to use this entanglement. It's more complicated than the previous figures, okay? But I will not do that, because in the lack of time, I want to discuss a couple of applications quickly. This is the timing I was mentioning. Okay, if you look at the red lines, you see that if the speed of light is 300,000 kilometers per second, in the fiber optic cables, the speed is 1/3 of that. If we assume that the length is less than 10 kilometers, then taking into consideration the decoherence formula of photons, within 10 kilometers, it's pretty good. Still we can use them, but after that, the photons decohere rapidly exponentially. So the bottom line is, for 1,000 nodes in a network, the entanglement swap time, the entanglement distribution takes less than 1 millisecond. With the data we have gathered from there's experiments around. Okay, quickly this, but I will skip it. These are the applications I want to discuss. I already discussed teleportation, maybe the key distribution quickly. This how entanglement can help with the key distribution, quantum key distribution. Basically, we have streams of qubits, A and B, which are sent by Victor to Alice. And we have only qubits A and qubits B now, Victor and Alice. And what Alice and Bob are doing, they measure their corresponding qubits in computational basis, either the rectilinear base or the rotation basis, and they do this basing selection randomly, independent of each other, okay? Then they check through the public channel if they have disagreement or agreements in measurements. Whenever they have agreements, they accept the result. If they have disagreements, they reject the result. And this way, any acceptance produces N1 and rejection is 0. So this way, they produce a key, a string of these qubits produce a key, a cryptographic key. Why is this secure? There have been a lot of studies of the security in terms of eavesdropping and attacks, and indeed it's quite secure, provided that the length of the key is reasonably long, meaning more than 100. Because an attack can succeed in 1 qubit to disturb the key by 25%. However, this rate of disturbance decreases exponentially with the number of qubits, and e to the minus n goes like that. So with 100 qubits, the disturbance or the attack effect is minuscule. Cryptographic conferences quickly, they will be in my slides basically. So what you do here, you have a group of people and they want to share a key. It's pretty much the same cryptographic key generation between Alice and Bob, except you can do it among a lot of people here, and they can share the whole key for communication among themselves in a group of people in a conferencing, and nobody else outside of the group knows, okay, the key. I will skip this quantum network repeaters. Okay, basically I discussed quite a few things about that, and this is the view of the future in quantum networking, at least the DOE, the Department of Energy view. This is actually the Long Island on the map, and this is the nodes of the quantum network, which will be here and there and expanded all over the country. But other countries are also working. This is the quantum nets in China, which they're doing out of strides. And I don't have a corresponding picture in Europe. I do have it, but I didn't put it there. So there's a lot of effort in quantum networking. To finish, I would say that quantum networking is quite close, okay, because a lot of experiments have been successful already, and it's quite close. Maybe we're closer to do networking, okay, before doing computation. However, let's also say the quantum nodes of the network are small quantum computers. Okay, not as big as the big ones that other speakers will discuss, but there are quite a few capable nodes. Okay. Yeah. All right, with that, I will thank you very much
Chris.
for your attention. Sorry for taking the time.
No worries. Yeah, we have 2 questions in the chat. Chris, just due to time, I'm going to let you answer those in the chat. I know one of them was about current implementations of quantum teleportation. I think as you've shown here, there are actually several quantum networks already being built and have already been built. So
what's the question?
Chris, I'll let you answer those in the chat if you want to.
In the chat. So I should go ahead and do it essentially offline.
Yeah, okay, I'll do that would work. And then our next speaker is Robert Loredo from IBM. So Robert, if you want to go ahead and share screen, excited to have you with us.
Thanks. So let me do that. Put it in full screen mode and get going. Okay, here we go. So I'm kind of happy that most of the other speakers spoke on a lot of stuff. So it brought some of the slides I was going to show down a bit. So it's great. So just to kind of give you all an overview from a research implementation side, right? So a lot of the computation, particularly for quantum computation, it's just that, it's computation, right? It's anywhere you do any kind of computing, there might be some potentials for quantum. Now, not all of them are going to be have potential for quantum, but there's a majority that we're looking into in various different industries and different domains that do qualify. We're looking at things like chemistry, in manufacturing, in life sciences, healthcare, as well as in financials, and of course in artificial intelligence, machine learning. So based on the kind of question that we had, or at least the first topic that we're discussing as to why quantum, it generally does come to this, right? So what kind of problems can we address where we can address easily today versus what we can with quantum versus classical? So there are certain problems. So for example, multiplying two large integers, let's say 2,000-bit integers, we can do that very fast on a classic system. A quantum system might actually take a longer time to do that. But those are things that we do that pretty well. But now if you get that problem and you reverse it, now you say, instead of giving you 2 numbers and ask you to give me a product, I'm going to instead give you a product and now ask you to give me the 2 factors that factor into that product. That gets very difficult for a classical system. In fact, very intractable. In fact, we discussed earlier today in a presentation that Shor's algorithm is an optimal way to do this using quantum systems. So there are problems that are beneficial one versus the other. So it's not too easy. It's just more to clarify, not to say, all right, let's grab my entire algorithm, my machine learning algorithm, just throw it over to quantum. It's not a lift and shift, right? There are particular components within your machine learning or artificial intelligence application that might run more optimal on quantum systems. So this is basically one thing that I want to make sure that everyone understands, is that it's not just a full quantum lift and shift from one to the other. So we're starting to talk off here just more on the technology. Over the past few years, as you can see here, we've been extending our hardware. We pretty much manufacture everything from the ground up. I mean, we build the quantum qubits, we build the processing units, the systems and hold them. Of course, through Qiskit, we're developing the software. We have our services teams, et cetera, that kind of work in all of these different areas. So because of that, we have a lot of tight integration with a lot of things that are coming up and obviously expanding. So as you can see here, this is our hardware roadmap. Right now, looking since 2019, we've had some very good key advancements in a lot of the technology, from our 27-qubit device, which is our Falcon, that was released back in 2019. This is the device that started off at 32. We had one particular device that was at 32, quantum volume of 32. We applied some of the error correction or error mitigation techniques and into the software, so that raised it up to 64. We made more enhancements, and it went from 64 up to 128 as a quantum volume. So we're always advancing both on a hardware as a software. The following one, last year, we had our Hummingbird 65-qubit device that came out. And then later this year, we're planning to come out with a 127-qubit Eagle processor. And this one here has more novel packaging and controls that we can use within these particular devices. And in development for next year, we're looking at a 433-qubit Osprey device. And this one here is we're focused, the key advancement is on miniaturization of components. Now, 2023 is a very important year, at least for us, in a sense, we're looking at it as a very much of an inflection point, because this particular process we have coming out, the 1,121-qubit Condor processor, is not only a larger processor compared to the previous ones as far as number of qubits, but it's also the key advancement here is integration. Meaning that all the previous devices that you see here, they're all single devices on a single system, right? So it's one quantum processing unit on one quantum system. But here, what we're doing is we're putting integration into these components. In other words, now that we can have this particular processor, we can now stack them, right, and integrate them with other systems. And this, of course, will then help us get to that path of 1 million qubits and beyond, these sort of very large scale systems, because of how we can now stack them up, as you can see here in the last slide, and how we can build this now infrastructure because of all these extra devices and the integration. We can have an infrastructure that connects all of these processors together, as well as look at the things as quantum error correction. So the advances on our hardware moving quickly. So the current device we have right now is our Quantum System 1, which you see pictured here. It's a large device. It's completely contained within the system, so that eliminates as much noise as possible. If most of you have seen the earlier pictures of quantum, you remember they're in a lab, they're in a very big noisy area. But what we've now done is put them in this commercially integrated box. So this is actually a first commercially integrated quantum computer. And it's in a box, it's self-contained. You can see it's on a raised platform. That's so to eliminate any kind of vibration or radiation or heat from the ground. The glass is tempered, so it eliminates any noise or vibration or heat to come in and affect the system. And that sort of black wall behind that dilution chamber, which is hanging from the top, that's where all the electronic components are. And we basically just stripped out all the components to specifically the ones that we need and put them in the back. This way, we're trying to isolate as much as we can from those qubits, because of course, any little noise or effects from the environment can affect that particular performance. Now, looking forward, as you recall from that Condor process, we're going to have now integrated processors. We want to be able to make sure that we keep them also isolated and very well integrated and clean. So we're developing this here super fridge you can see here, which is basically the first of its kind, and as opposed to the other one that you see previously in the slide before this one, it's where we can stack. So inside of that container you see in the middle is where we'll have all of those stacked processors, and we can go from 1,000 having just one up to 1 million and beyond from there. And the super fridge basically is so that we can keep that the processors down cool to 100 millikelvin, so that we can make sure that the processor is at operating temperatures. Of course, by having more of them in here rather than having one for every processor, we do save a lot of time. Now, of course, this is just a thing that keeps it cool. It's not actual the quantum computer itself. That's within that little small processor that we have. Now, that's the hardware. Now on the software. So we're within the Qiskit community and the Qiskit development team that we have. We're obviously trying to integrate and make Qiskit as easy as possible to be able to leverage and use, so that you as a researcher, you working in some domain, whether it's finance or chemistry life sciences or machine learning, data science, using a particular quantum computer shouldn't be any more difficult than doing something as simple as this. You import your libraries. You say, I want to load my data. Here's my data that I'm getting, whether it's financial input or anything, any kind of samples. You load that data into an object. You define your runtime, what quantum runtime you want to run, and you pass your API token. Just say, okay, these are the devices I have access to, all the runtimes. This is what I want. Now in that runtime, I want to run this particular type of program, quantum program, on this data. Whether it's quantum program can be quantum support vector machine, a quantum neural network, a energy ground state or something, etc. You're just basically calling it by its name, passing in your data, and it's going to give you back your results. Simple as that. So you don't have to worry about doing too many things under the covers, because that's going to be done by other levels of development. So from a researcher perspective or end user, this is ideally what we want to do, particularly when we get to these 1,000 qubit computers in the near future here. So how does all this ecosystem kind of work together? So there's different levels. At the first level, at the kernel level, this is basically where they're working at the circuit level. These are working on pulses and timing controls between the hardware device, actually how it's run, since we're using on superconducting qubits. Is how do you run those particular pulses, get the right angle, get the right timing so that we can run, so it's very efficient and free of any errors. Above that level, you have algorithm developers. Now, these algorithm developers get those kernels, those pulses, those circuits, etc., those dynamic circuits, and then pull them in together and basically prepare these states. So you have some algorithm based on some data, you have some operators, maybe it's a structured search, so you have to set up some certain oracles on them. But you're basically, in general, just using all of these building blocks to construct these algorithms. And the algorithm could be something specific for something. Let's say it's a structured search, so there's something like Shor's, or if it's, or rather Grover's, or if you're using some factorization like Shor's or whatever other algorithms, some Monte Carlo simulations, some looking for a quantum kernel estimators. Those are all developed on the algorithm development component. And then following from there, we have, oops, I think my slide's right, there we go, with the model developers. So they're the ones that are basically going to grab these algorithms and develop these models. So these models are basically going to be what we saw earlier here. It's going to be something that's going to be used by someone who's not necessarily an expert in quantum, but just wants to use a quantum computer to be able to run some application or run some algorithms to be able to, to solve their problem. So all they would have to do, in a sense, is be able to just describe their problem, rather than that old other way, which is I want to describe my solution, how I'm going to solve this. Is more like, here's the problem I have. I want to simulate this on a Monte Carlo. I want to simulate this stuff on a traveling salesman problem or something. You describe your problem, you use the model, and the model will give you back the results. So that's on the different levels. So from that, it was on the development side is one point. Dynamic circuits, so this is something that's within the platform itself, the infrastructure. So there's some algorithms that require certain adjustments, like for example, a variational quantum eigensolver. That basically is you run, it does some simulation, grab some results that come back from your measurement, you run an experiment, you run your results, it comes back, you look at the results, and then you make an adjustment and you run it again. So on the top graph here, you can see you have your laptop, you have your circuit, it goes across the cloud, and then when it gets in there, it gets connected to the hardware, it prepares the states, it runs it executes your quantum circuit, and then it gives you back your results of zeros and ones. Now, when you get back those results, there's going to be some adjustments you want to make. So you make those adjustments, and then based on some conditions or constraints of your problem, and then you run the circuit again just to optimize it. These are things that you kind of would do, for example, variational quantum eigensolver, Monte Carlo simulations, etc. The problem here is, of course, that you have a lot of overhead here in the cloud, right? Then when it comes through here, it's got to prepare the states again with these new values. If there's a queue, you got to wait in the queue. It just takes a long time. So the dynamic circuit here, the way this works at a Qiskit runtime, which is what's built underneath this, takes care of that. So by using a dynamic circuit now, you're passing a circuit with all the information. However, this time, all those constraints and all those conditions and variations are done closer to the device. So there isn't any looping back. So you're not coming back here if you have to run this 20,000 times or what have you. You don't have to go through and build up all the overhead. It just does that all locally here. So when you're at the device, it checks the measurement. It says, if measurement of the qubit 7 is 0, then do this and run it again. If the measurement of qubit 64 is 1, then run it again using these updates. So it does that much closer, so it saves you a lot of that overhead. And we've done these with some of the earlier computations we did, particularly around chemistry. And we noticed that was something that took 11 weeks. only took a few hours. So we measured around 100 to 120 times speed up on just getting rid of this overhead in a sense. So there's a lot of work that's obviously being done, not just on the algorithm development and development of the cycles, but also on the runtime itself. Again, it's just to optimize this as much as possible. So putting all this together, how does this look like? So you can see here from the bottom, building coming up, we have our quantum systems. So we're updating them as we go. And you can see here's where we have the condor, where we have that inflection point. So as we're building up, the kernel developers, they're working on circuits. Now they're working on this Qiskit runtime, which you're seeing here now, which is being released. And then we're looking into dynamic circuits. And these are things sort of having, again, these other conditions and these other operations you could do on the device mid-circuit. So that's where those are going to come in. Algorithm developers are already working on these different types of algorithm application modules. So they're looking at natural sciences, finance, optimization, and machine learning. So they're developing the quantum neural networks, quantum support vector machines, et cetera, et cetera. Then as we get to the larger devices and moving into the Condor processors, then we're looking at things like circuit libraries, because right now we can measure things at this individual circuit and qubits, and saying qubit 1 goes to qubit 2, qubit 3, et cetera. But as the processors get larger and larger, particularly we're talking about 1,000 or thousands, hundreds of thousands of millions of qubits, you got to look at it from a circuit library perspective. You can't look at qubit by qubit anymore, entangling this qubit with that qubit. It just has to be involved a lot quicker. So the circuit libraries will help do that. And by doing that, we also have these pre-built quantum runtimes, which the algorithm developers will do. Because now that we have libraries, we can pre-build a lot of these particular runtimes that are specific to those particular domains. There might be some types of runtimes that might work one way with optimizers or in finance or machine learning. It'll all vary. So the pre-built quantum runtimes will be defined for those algorithm developers. And of course, finally comes up to the model developers, and they'll get all those pre-built runtimes and all those models and generate their models. Like it's okay for this runtime, which is very functional for machine learning in the area of finance. Let's say it's like fraud detection versus this machine learning, which is more on classification, or maybe on neural networks, which will be at a different type of domain. So these runtimes, the model developers can use those runtimes to build forward. And of course, this is how we're modeling these development roadmap moving here in and beyond. So we got the technology, we had the hardware, we had the software, we're looking at the technology, how to optimize the infrastructures around it. But now, of course, we have the technology, but we need to really know how can we engage this? How can we run these on the device? What kind of problems can we solve? And this is why we developed the IBM Quantum Network back in 2017, just after we released the first quantum computer, is for that reason. It's like, all right, we need to go to the experts, the industry, to say, okay, where can we most optimally use these things? Where do we see the potential in quantum computing? How do we know what particular types of problem that we need to solve? Where do we optimize? So engaging industry is very, very important. So since the IBM Quantum Network started back in 2017, we have since grown. We have over 157 total members. 12 of them are industry partners. So you can see that we got them all different types of industry: Accenture, BP, Boeing, Daimler, ExxonMobil, Goldman Sachs, JP Morgan Chase, etc. We have various different hubs, and these are basically extensions of the IBM Quantum Network. So you can see we have here Fraunhofer, we have CERN Open Lab, lots of different individual national labs, as well as universities in different areas. We also have members, and these are folks that are linked to hubs, and they work with them on various different types of research projects. You can see we have GE Global Research here, different National Institutes labs, Lockheed Martin, again, various different things, Sony, different industries, different domains, manufacturing of Toyota in here as well. And of course, a lot of startups, because we do have a lot of startups that are working on different areas of quantum, both hardware, software, services, et cetera. So you can see a lot of them listed here. And when, of course, this is also growing, and they have access to our devices and to be able to expand their own industries. And of course, down here at the end, the academic members and partners, which go everywhere from Florida State, we have University of Minho, et cetera, et cetera. So in this group, this network continues to grow because, again, it's one thing that's called technology. It's working with all of these different industries, different partners, different hubs and members and startups, so that we can expand the technology at a much more rapid pace. Now, working with these industries, obviously, there's a lot of maturity that goes through them as far as developing their research, but also developing, new techniques and new advances in their own industry, albeit it's in a small size at the moment because we're all demonstrated using that.
My apologies for that. I dropped off there for a second.
And of course, you can see here by that circuit, they looked at energy of a binary crystal